In this video, we're going to talk about the acidity of alkynes and how to prepare alkynes from elimination reactions. Now, these are really two separate topics, but because they're both fairly short, I thought I'd combine them into one video. So you may recall from earlier in the semester when we talked about acids and bases that alkynes tend to be more acidic than alkenes or alkanes, right? And when we look at pKa values, the lower the pKa value, the stronger the acid is. And so a 19-point pKa difference between acetylene and ethylene means that acetylene is 10 to the 19th times stronger as an acid than ethylene. Due to the fact that alkynes are acidic, they can be deprotonated if I use a sufficiently strong base. And when we think about acidity, when we did it qualitatively, remember that we use the acronym ARIO, where A stands for atom type, resonance, induction effects, and orbitals, right? And we talked about acid strength qualitatively. We said an acid would be stronger if its conjugate base was more stable. And when we think about alkanes, alkenes, and alkynes, and we look at the conjugate bases that we'd get from deprotonating each of these, in the case of an alkane, the lone pair that we produce from the deprotonation is located in an sp3 orbital versus an sp2 orbital for an alkene and an sp orbital for an alkyne. And you can see that when we go from sp3 to sp2 to sp, these hybrid orbitals get smaller. And the smaller the orbital is, the closer those lone pairs can reside to the nucleus, which is going to make it more stable. And so that's why alkynes are more acidic than alkenes and alkanes. When we talked about the strength of acids and bases quantitatively, we used the pKa value of the acid to rank them in terms of strength, right? And so the lower the pKa value, the stronger the acid. And in general, when we think about acid-base reactions, it's sort of a competition between the acids to donate protons or between the bases to accept protons. And generally, when we're doing this quantitatively, we use the acids because it's usually the pKa's that we're given, not the pKb's for the bases. And so the stronger acid is the better proton donor, and so that will force the equilibrium to the other side. So because acetylene has a lower pKa than ammonia, that's going to drive the reaction to the other side, and so that means ammonia's conjugate base, NH2-, is a strong enough base to deprotonate the acid. And so if you're asked, is a base strong enough to deprot an alkene, what you want to do is compare the pKa's. So compare the pKa of alkynes, which are about 25, to the pKa of the conjugate acid of the base we're trying to use. If the pKa of the acid is bigger than the pKa of the alkyne, then that base is strong enough to deprotonate the alkyne. Right? If we use hydroxide as an example, the conjugate acid of hydroxide is water, right? And because water has a lower pKa than acetylene, right, that's going to force the equilibrium to the left, and so hydroxide is not a strong enough base to deprotonate an alkyne. What you'll see most often, the base that we'll use to deprotonate alkynes is NaNH2, but this is just one example, and many other bases can be used as well. As an example, here's a list of potential bases that we could use to deprotonate the alkyne. And so what we need to do is look at the conjugate acids of each of these bases, which we have on the right. As long as the pKa of the acid is above the pKa of the alkyne, so as long as it's above about 25, right, then all of these bases can be used to deprotonate an alkyne, right? These bases are not strong enough. The pKa's of their conjugate acids are too low. So at the end of this video, I'll have an example about the acidity of alkynes, but I want to change gears now and talk about how to make alkynes from elimination reactions. So we learned in a previous chapter that if I have an alkyl halide and I react that with a strong base, I can cause an elimination to occur which produces the alkene. Well, if I have an alkyl dihalide where I have two halogens attached to my carbon chain, then when I react that with a strong base, I can produce an alkyne. So the mechanism is the same as we saw for the elimination of an alkyl halide to form an alkene, and they generally proceed by the E2 mechanism. So in one concerted step, the base captures the proton, those electrons form the double bond, and then the halogen acts as a leaving group. If I come in with a second base and I have a second leaving group, right, I can do the same thing. In one concerted step, proton transfer, we form the triple bond and the loss of a leaving group. And the halogen atoms can either be on the same carbon as they are in the first example, or they can be on adjacent carbons as they are in that second example. Okay, so if we have an alkyl dihalide, when we react that with a strong base, we can produce an alkyne. But one issue that we need to be aware of is when we form a terminal alkyne, right, where we've got a hydrogen connected to the carbon-carbon triple bond. We learned earlier in the video that if I react this with a strong enough base, I can deprotonate it. And so very often, if we have a base that's strong enough to cause the double elimination to form the alkyne, it will also deprotonate the alkyne we were trying to create. So a way to get back to the neutral alkyne is to react that with an acid. And it doesn't have to be a terribly strong acid, it just has to be a stronger acid than the neutral alkyne. So as long as the pKa of the acid is less than about 25, it will do the job. And so the most common acid that we choose is just water. So water is sufficient to reprotonate our ion to form the neutral alkene. All right, so sort of the take-home message and what I'm going to add to my reaction journal. If I have excess strong base, and so excess means excess strong base. So if we have a lot of strong base, and the most common base that we use is NaNH2 dissolved in ammonia, I can cause the elimination of an alkyl dihalide to form an alkyne. And then what you'll see, if we're trying to produce a terminal alkyne, after we add the excess strong base, we'll typically add water, as we saw on the last slide, to go back to the neutral alkyne instead of the deprotonated ion. Okay, so let's look at a couple examples. So we're given two strong bases that we've previously used, and we want to know if they're sufficiently strong to deprotonate a terminal alkyne. So to answer this question, we need to determine if the pKa of the conjugate acids of these bases is bigger than 25. Right, the pKa of the alkynes is about 25, and so if the pKa of these bases is bigger than 25, then these bases are going to be strong enough to deprotonate that alkyne. So if we move down a little bit, and then let's make this a little bit bigger, right, so here is my tert butoxy. And then this is its conjugate acid. So the conjugate acid has a pKa of 18. So that means that this base is not going to be strong enough to deprotonate the alkyne. And so the tert butoxy is out. But then it's not in this table, but the pKa of H2, which is the conjugate acid of H minus, right? Remember the other base was NaH, right? So the sodium is really a spectator ion, right? So our base is really the hydride ion. Its conjugate acid is H2. That has a pKa of 35, right? That's bigger than the 25 that we need, and so this base is strong enough. NaH is a strong enough base to deprotonate an alkyne. Okay, so one last example. We want to predict the products and draw the mechanism for the following reaction. I have an alkyl dihalide. I have a strong base, and I've chosen the strong base that we'll typically use and that we'll see in examples where we're going to convert an alkyl dihalide into an alkyne. So my products, I'll get my alkyne. I have the isopropyl group coming off one side, and then on the other, right, I have one carbon and then the benzene ring. So here's my one carbon. And then the benzene ring. Okay, now for the mechanism. So I'm going to have two E2 reactions. So remember, the sodium is just a counter ion. Right, the base I'm really interested in is the NH2 minus. Right, I need to draw in the hydrogens for the elimination in order to draw the mechanism properly. So my base will steal the proton. That'll form the double bond. We'll have the loss of a leaving group. So I'll get an alkene. And then on the other side, I'm going to be lazy and just write the pH for the benzene ring. And then for the second elimination step, right, I do need to show this hydrogen. Right, we'll react with another base. So that base will steal the hydrogen. Those electrons become the second pi bond, the loss of the other leaving group, and then we'll get our products.